we want to add some of the terms of a sequence together. And for this video, we're going to talk about adding up terms of an arithmetic sequence. So let's jump in and start with this sequence. Suppose we have 4, 11, 18, 25, and so on. And you can confirm that this is arithmetic because we have a common difference. 11 minus 4 is 7. 18 minus 11 is 7, and 25 minus 18 is 7. And let's suppose I want to find the seventh partial sum. In other words, S sub 7. Remember, that means we're going to add the first 7 terms of this sequence together. So for this one, it doesn't take much to do that. We could just do it directly. We know the first 4 terms are 4, 11, 18, and 25, but certainly we could find 3 more because we can simply add 7 to each term to get the next one. So if the 4th term is 25, the 5th term is 32, and the term after that is 39, and the 7th term would be 46. And then we can simply grab a calculator or just go through and add left to right in our head, and we'll find that that sum is 175. But suppose the question hadn't been to find the sum of the first 7 terms. What if it had been to find the sum of the first 70 terms or 700 terms? It's not always reasonable to just be able to write out a list to find the sum. So let's find this sum a different way, just using a little cleverness here. And let me show you how it could be done. I'm going to write the 7th partial sum again as 4 plus 11 plus 18 plus 25 plus 32 plus 39 and plus 46. And let me write it a second time. And this time, as I write it down, I'm going to write the terms in the reverse order. So I have 46 plus 39 plus 32 plus 25, and then we have 18, 11, and 4. Now, if I add these 2 equations together, I would have twice the 7th partial sum, and that would equal 4 plus 46, that's 50. 11 plus 39, that's 50 again. And I have another 50 and another one. And I can write this. So we have 7 50s that we're adding together. So we have 2 times the 7th partial sum is equal to 7 times 50, or the 7th partial sum is 7 times 50 divided by 2. And if you do the arithmetic here, you'll see that you have 350 divided by 2, which is 175. So we get the same answer. And for this particular problem, it's a longer process. But the idea that we used here is actually going to get us to the formula that we're going to need in the event that we needed to add 70 terms or 400 terms or 10,000 terms together. I want to point out right here that the 7th partial sum right here was 7 times 50, and the 50 could be thought of as coming from this 4 times this 46. In other words, the first term and the 7th term in the sequence. We have 4 plus 46 divided by 2. So let's look at this. So to find the sum of the first 7 terms of this sequence, we have 7 times the sum of the first term and the seventh term, and then we divide it by 2. And we're going to see something similar when we do this in general. So let's do that in general right now. So we're going to let the sum of the first n terms of an arithmetic sequence be a sub 1, a sub 2, a sub 3, and so on, all the way out to a sub n. So the sum of the first n terms are, I wrote that a little bit high here, are a sub 1 plus a sub 2 plus a sub 3 plus, and we'll go all the way out to a sub n. Now we're going to write it again, s sub n, and we're going to write it backwards like we did in the previous example. So we have a sub n plus, the term prior to that is a sub n minus 1. The term prior to that is a sub n minus 2. And we keep going until we get to the first term. And when we add those two equations together, we have 2 times s sub n equals, and look here for the first term, we have a sub 1 plus a sub n. And notice over here, we have a sub 1 plus a sub n. But as with the previous example, all of these will have that same sum as well. And when we count how many of these sums we have, there'll be 1, 2, 3, all the way out to n. So we have 2 times s sub n equals n of those sums. And we can divide by 2. We have n times a sub 1 plus a sub n divided by 2. And here's the formula that we want to know that we can use when finding the sum of the first n terms of an arithmetic sequence. This ended up being the same term, same value each time because we had an arithmetic sequence. If this had been some other type of sequence, this formula wouldn't have worked out the same way. We wouldn't have had that same sum along here. So remember, this is a formula that is only valid if we're finding the sum of the terms of an arithmetic sequence. But now let's practice using it. In a previous video, I had finished the video with this particular sum, and I said, hey, after we talk about arithmetic sequences, we would be able to find this sum. So I want to do this problem now, and if you haven't watched that video, that's totally fine. Let's jump in and do it. So remember, with sigma notation, we substitute in 1, and then 2, and then 3, and then 4, and keep going until you get to 350. So I'm not going to represent all 350, but let's jot down a few. So we substitute in 1, so we have 4 times 1 plus 1. We substitute in 2, 4 times 2 plus 1. Let's substitute in 3, 4 times 3 plus 1. And then we would keep going, and let's substitute in the last term. It is 4 times 350 plus 1. And let's write what this sum looks like. 4 times 1 plus 1 is 5. And then we have 9. And next we have 13. And we would continue until we get to, what is that, 1401? Do I have that correct? Let me grab my calculator wherever it went. And where did it go? Well, we'll just trust that I have that correct right here. Let's see, 350 times 4, yep, that seems to be 400. 1400 plus 1. So this is what we're trying to find the sum of. Notice it is arithmetic. Each term is 4 greater than the previous term. So now we can find the sum of these numbers by using our formula. In this case, notice we're adding 350 numbers together. This was the first term, second term, third term, 350th term. And our formula is this. So when we substitute in 350, for n, we have 350 times the first term plus the last term. And by the last term, I mean the 350th term, divided by 2. So now we have a little arithmetic problem to do. Now certainly we can do the 5 times 1401. Don't need a calculator for that. 350 times 1406 divided by 2. And we could do more simplifying even without a calculator, but I have a calculator in front of me now, so let me just punch this in. 350 times 1406 divided by 2. So the sum of those 350 terms is equal to 246,050. And I'm certainly glad I didn't have to go through one by one to add those terms together. And remember, we were able to use this formula because this was arithmetic. Let's do another problem. The next one I'd like to do is this one. Find the 70th partial sum for this particular sequence. So we know we need to use this formula. S sub n. Oh, but before we do that, let's confirm it's arithmetic. It's a serious mistake, actually, to use this formula if we don't know it's arithmetic. And notice the difference between these two is 7. Difference between these two is 7. Difference between these two is 7. So we do know that we have an arithmetic sequence. So we know the sum of the first n terms is n times a sub 1 plus a sub n divided by 2. Conveniently, we know n is 70. So I substitute in 70. The first term is 4. But, oh, I don't know the 70th term. Let's just write a sub 70 right here. And we're going to divide by 2. So I don't know the 70th term. But fortunately, we have the formula that relates the terms of an arithmetic sequence. So in this problem, we need both of these formulas. Remember, here's how the relationship between the first term and the nth term of an arithmetic sequence. It looks like this. A sub n equals a sub 1 plus n minus 1 times d. And notice we know the first term, we know how many terms we have, we know what d is, and that will allow us to find the nth term. So let's substitute in 70. Our first term is 4. We have n minus 1. N is 70, so n minus 1 is 69. You can write that 70 minus 1, or I might as well just write it as 69 times d, which we know is 7. And now we can do that arithmetic. So we have 69 times 7. And then we're going to add 4 to that. So I know the 70th term is 487. And I like to look at the sequence and make sure that it seems about right. The numbers are getting bigger, so 487 seems about right. If I had gotten a negative answer, for example, or 2 trillion, I would be suspicious that something didn't go correctly. But now we know the 70th term. The 70th term is 487. Let's substitute it into our formula. So we have 70 times 4 plus 487 divided by 2. And now we have an arithmetic problem. So I have 70 times, let's add those together, 487 plus 4 is 491 divided by 2. Sometimes I do even a little bit more before I grab a calculator. The 2 goes into the 70 evenly. And so that's 35 times 491, but you don't need to. You can just grab your calculator and throw these numbers in. So we have 35 times 491. And we get 17,185 is the sum of the first 70 terms in this list. Let's do one more. We're going to find this sum. Let's confirm that we have an arithmetic list here. 984 is our first term, and then we subtract 3 and we get here, subtract 3 and we get here, subtract 3 and here. So yes, it is arithmetic. So again, I know I can use this formula. The sum of the first n terms is n times a sub 1 plus a sub n divided by 2. This time, I know the first term, it's right here, and I know the nth term, but I just don't know in what position this term is. Is this the 20th term, or the 300th term, or the 117th term? That's important because that's our n value. Remember, these are actually the values of the terms. N is the spot that number is in the list. So my formula, just substituting in what we know, looks like this: 984 plus 51 divided by 2. But again, I don't know how many terms I have. And that brings me back to that other formula again. These two formulas get used in conjunction frequently, and it's our other one that we have for our arithmetic sequences, and it relates the terms to each other. The nth term and the first term are related this way. So we know the nth term is 51. We know the first term is 984. We don't know n, so we'll leave n minus 1 in there. And d, what was d? D is the common difference. Remember, you take one term and subtract the previous term. So our d value is -3. And now we have a linear equation to solve. Sometimes people distribute that -3. I usually don't, and I'll show you why in just a minute. I'm going to subtract 984 from both sides. So I have 51 minus 984. So that's -933 equals n minus 1 times -3. We know n is going to be an integer value because it's the number of terms that we have in this list. So I know if this is an integer value that -3 is going to go into this number evenly. So I often solve the equation by dividing by -3 right here. And by the way, that is not something that you need to do. If you feel more comfortable distributing that -3 and solving the linear equation that way, go ahead and do that. It doesn't matter. But I'm just going to divide both sides by -3 this way. And if we divide 900, both of them are negative, notice, so we'll have a positive value. 933 divided by 3, we get 311 equals n minus 1. So that means n is 312. So I know this is the 312th term in the list of numbers for this particular problem. So using that value over here, I have the sum of the first 312 terms is equal to 312 times 984 plus 51 divided by 2. And let's see, 984 plus 51 is 1035. And we're going to divide that by 2. So let's just do that arithmetic. 312 times 1035 divided by 2 equals 161,460, and we have the sum of this expression.